Okay, so let's start. The next topic which we are going to cover is the logistic regression. Now, first of all, starting with the section 1, why logistic regression? So, first of all, as we all know about linear regression, it predicts continuous value like predicting household prices, temperatures. But now, what happens when you have to classify the output in categories? For example, email spam or not spam, or type of tumor, or will the student pass the exam or fail. In those categories, we don't want a type of number, we want probability, something between 0 and 1 that can be mapped to a classical label. Okay, so for that we need logistic regression. Basically, logistic regression is interpretable, probabilistic, and because the loss function is convex, there is only one global minima, means gradient descent can always find the best solution for it. There can be one more quick question also, that logistic regression, you need to understand this, that logistic regression, being having a name as regression, is a classification algorithm. Okay, so now let's move to section 2, the sigmoid function. Okay, so when we are talking about the logistic regression, the main part is the sigmoid function. The formula for sigmoid function is sigma of z equals to 1 divided by 1 plus to the power of minus z. Okay, here z is just the linear combination of your input features, which we have seen in the previous video, like y equals to theta naught plus x1 theta 1. So that we have written in the vector form, theta transpose x. Okay, so now the most important question is that why sigmoid is so special. Okay, no matter that how value you give it to it, positive infinity, negative infinity, the output will always stay between 0 and 1. So this is one of the most important property for the sigmoid function R. And with that, there are some of the more properties. For example, at z equals to 0, sigma value equals to exactly 0.5, and this will be our decision point to classify that. For example, let's take an example of a cricket match, that will India win today or will lose today. So what we are going to do is we are going to classify the point of the previous data, above 0.5 and below 0.5. So 0.5 will be our decision point, and thus how we can do the classification that we can call as logistic classification. The function is very symmetric. Sigma of minus z equal to 1 minus sigma of z. Okay, so that's also an important thing. As third point is that as z goes to the positive infinity, sigma approaches to 1, and as z goes to negative infinity, sigma approaches to 0. So it has a boundary condition which you can see that we can understand here. Thirdly, we have the formula written for this, the classical derivation, that can be important for some of the institute exams and all that. The maximum value of the derivative that we can go through the quotient rule is 0.25%, 0.25. That can be, you need to remember this, and this value occur at z equals to 0. So now moving towards the section 3, that is the hypothesis function and the decision boundary. Okay, so now we have a hypothesis function which we can denote as p hat. The formula is given here. Now the most important thing is that why we need this hypothesis function. Okay, so here's the clever part, that p hat is greater than or equal to 0.5 if and only if the theta transpose x is greater than or equal to 0. Okay, so now the decision boundary is more simpler and can be related with theta transpose x equal to 0. Okay, for a 2D problem with two features, the given this gives you a straight line. If you add polynomial feature like x1 square plus x2 square and all, you can get a circular and an elliptical boundary. Okay, so this is also an important part that you need to remember is that for the 2D problem you get a straight line, and for the polynomial you can get the elliptical and the circular boundaries. In section 4, moving towards the section 4, we have the log loss. Basically, now what is log loss? Okay, the answer, if you plug in the sigmoid function into the MSE, mean square error, the result of the cost function become non-convex. Okay, full of local minimas and all that. So the gradient descent gets stuck here, so that's a disaster. So in that case, we have to use binary cross entropy, also called as log loss. Now we have the given formula, so now let's break down it. When the true label is 1, the cost is minus log of p hat. If a model predicts p hat close to 1, then cost is nearly to 0. That's great. But if it predicts close to 0, then cost shoot to infinity. That's a very heavy penalty to us. Okay, and taking this on the other side, when the true label is 0, the cost is minus log of 1 minus p hat. So that's the same idea but in reverse. The most beautiful thing is that the log loss is a convex function due to which it guaranteed a single global minima. Okay, now moving forward for the theory, if you want to go more into detail, then there is maximum likelihood estimation of the Bernoulli distribution labeling, and that's completely a mathematical ideation of minimizing log loss function. Okay, moving forward to the further section of the gradient descent, let's talk about the optimization. And to find the best theta, we have to just take the gradient of j with respect to theta j. Okay, we got a formula, and the fun fact that if you notice is that this look exactly like the gradient descent formula for the linear regression, but only the difference is that the p hat here is a sigma of theta transpose t, not a linear output. Yeah, so that's a very important thing which you can say that this has been a upgradation from linear to logistic. Now talking about the odds and the log odds, let's talk about how to interpret the weight. The odds of an event is p hat divided by 1 minus p hat. The log odds is also called as the logits, and it is one of that log of which equal to theta transpose x. You can directly solve it using the equation also. So basically what the model is actually showcasing is that model is actually a linear in log odd space. Okay, this is the geometrical interpretation if you want to say. Okay, so now we have about the weights interpretation. If theta j is positive, increasing xj increases the probability of class 1. Okay, and if theta j is negative, then increasing xz will decrease the probability of class 1. Yeah, so let's move towards the another section, that is section 7, the evaluation matrix. We have already covered all these evaluation matrix, the confusion matrix and all that in our previous videos: accuracy, precision, f1, recoil, AUC, ROC curve. AUC, ROC curve we will be covering in the other sections. Okay, so let's move forward towards the section 8, that is the multi-class classification. In multi-class classification, we have one versus rest, OVR. Okay, train k binary classifier. Each one answer is k a class or not. Okay, then predict whichever class gets the highest probability. We can use this in the softmax regression also, the proper generalization of the logistic regression to the k classes. The given formula for this is already written here. Now we have to discuss some of the key properties of it. For example, all the output probabilities have a sum to 1. For k equal to 2, the softmax reduce back to its regular logistic regression formula. Okay, and this loss is called as the categorical cross entropy. First we have taught about the binary cross entropy, and now we have the categorical cross entropy. So the second point is showcasing that only, that if we put it equals to 2 binary, then it can be the categorical cross entropy converts to binary cross entropy. The next section which we have is the regularization. We have talked about it in the previous lesson also. Now let's go in some depth. So the logistic regression may be overfit. Okay, now what is overfitting and underfitting, we're going to cover it, but just for now you can know that it's especially when lot of features or the polynomial expansion are present in a given function. Okay, so the regularization can be of two type: L1 regularization and L2 regularization. L2 is called as ridge regularization and L1 regularization is called as lasso. Now the ridge regularization is adds the lambda over 2 times the sum of theta j squared. Okay, so the theta naught which we have considered in the previous part, many of the books uses the lambda as a parameter multiplied by the square of m. Okay, so m is nothing, just the sum of the theta j, and squared of it is used in the ridge regression. Now what are the benefits of this is it shrinks all the weights towards the 0 but never exactly 0. This is very smooth and differentiable everywhere. And one of the most, that when we are working with the libraries in scikit-learn, this is controlled by the parameter C, which is inverse regularization strength. Okay, and next we have the L1 regularization, that is the lasso. It adds the lambda over m times the sum of theta mod of theta. Okay, now here you don't need to square it. Now some of the points are that it dives some weights exactly to zero. That's the feature selection built in. And secondly, it's non-differentiable at zero, so we use a subgradient method here. Okay, so here you can also see the difference between the two, and you can see that why L2 regularization, ridge regularization, has a edge over L1 regularization. Moving towards the section 10, we have some of the assumptions that we have to put on in the logistic regression, like the output must be binary or the categorical. Second, the log odds must be linear in features. Thirdly, observation must be independent of each other. No autocorrelation should be present. Fourth one is the no several multicollinearity that we can check via VIF score. We have talked about the VIF score in the linear regression model also. Now you have a large enough sample for it, roughly 10 events per prediction for a stable estimation. Sixth point is that no extreme outliner should be there. We'll be learning that how you can remove the outliners, that will be covered in the pre-processing stage. But before that, we can take it as an assumption. Now next we have, coming towards the end, we have here the wrap up for the logistic regression, that how a sigmoid function work, how a log loss function work to the gradient descent, and about the regularization and about the multi-class extension.